So we've been talking about wavelength modulated sensors in our last lecture, and before we go into specifics of wavelength modulated sensors, let me just go back and share you some information which I had forgotten to do previously. So when we were discussing phase modulated sensors, especially when we were talking about fiber optic gyroscopes, we were deriving certain limits as far as fiber optic gyros are concerned due to environmentally induced phase noise as well as short noise and all that. An excellent reference for some of this is actually from it's this I think it's probably a book chapter maybe, but fiber optic gyroscope principles by Merlo, Norgia, and Donati. So this actually so this is actually from the handbook of fiber optic sensing technology, and they talk about a lot of the basics of fiber optic gyros, where it's applied, and then going through the principles and all of that. So you may want to just go back and look at that as a reference. Okay, so coming back to where we were talking about wavelength modulated sensors, and we recognize that what we are really interested in is encoding the perturbation in frequency or wavelength. So this is actually the perturbation information that we are interested in. And the reason why we want to do that is because of the fact that when it's encoded in wavelength or frequency, it cannot be corrupted by all the traditional noise sources that we saw. For example, the environmentally induced noise. It's not an issue as far as wavelength modulator sensors are concerned, because it cannot change the wavelength information. So that's actually a big advantage for these sensors. And specifically, we started talking about using these fiber Bragg gratings. So let's go into that in a little more detail today. So we're going to be talking about fiber Bragg grating based sensors. So we'll first look at what these fiber Bragg gratings are all about. But typical configuration is going to be something like this. You have a broadband source that's emitting radiation over a broad range of wavelengths, and that is typically going into a circulator or a coupler, so that it's sending light in one particular direction, and we have a fiber Bragg grating that's connected to this circulator. So anything that's back reflected from the grating is going to come down this path. So if we say port 1, port 2, and port 3, it's going to come to port 3. And so port 3 typically has this information where if you look at the power spectrum, power as a function of lambda, it's going to look something like this. Okay, and we are interested in picking up this center wavelength. So how do you measure that? Well, we know that our traditional receiver is not capable of picking up color. So you have to essentially go through what is called a wavelength demodulator, right? A wavelength demodulator that converts essentially the wavelength information into intensity information, and then you can actually pick it up using an optical receiver. So that is typically the configuration that we are looking at. Now, there are several questions with this. First of all, if we talk about this reflecting at lambda b, what defines lambda b, what is that Bragg wavelength dependent on, and then you are interested in what is the width of this peak over here, what determines where it goes to zero, what determines the peak reflectivity level, right? So this peak actually corresponds to a certain reflectivity. So what determines the reflectivity of a fiber Bragg grating, and so on, right? So let us actually try to dwell into this a little more deeper as to what is the physics of fiber Bragg gratings before we go into how we can use fiber Bragg gratings as a sensor. Okay, so how does a fiber Bragg grating work? A simple way of explaining this could be this answer to this question of how does a dielectric mirror work? Okay, we know that dielectric mirrors typically have refractive index, different layers with different refractive indexes, especially a high refractive index layer followed by a low refractive index layer and then a high refractive index layer, and so on. So essentially it's when you look at a dielectric mirror, it's going to consist of multiple layers, right? So one layer with high refractive index, another followed by another layer with low refractive index, another layer with high refractive index, another layer with low refractive index, and so on. So when you have a wave coming in, right, it's going to undergo reflection whenever there is a change in the refractive index, whenever there is an impedance mismatch. And clearly when it's going from lower refractive index into a higher refractive index, from a rarer medium into a denser medium, it is going to undergo a phase change of pi, right? So in this case, for example, if you are looking at this reflected component, because it's going from air into this medium with a higher refractive index, it's going to have a phase change of pi. So a mirror is one, a well-designed mirror with high reflectivity is one where all these reflections from these different layers are going to add in phase. So how can that happen? Well, that can happen if, let's say, this is designed so that you have a propagation phase of pi by 2. Upon reflection here, there is, because it's going from high refractive index into low refractive index, there is no phase change upon reflection. But let's say this is actually another pi by 2 because it's going through the same thickness. So you have a cumulative phase change of pi, right? So these two components are in phase with respect to each other. So they add up, their fields add up essentially. Okay, and then you can do the same for the next layer also. So this is also pi by 2, but here you have pi phase shift, right? And because it's going from lower refractive index to higher refractive index, so you have a pi phase shift at that point. And let's say this is pi by 2, this is also pi by 2, and so what you get out here is pi by 2 plus pi by 2 is pi, plus pi is 2 pi, plus pi is 3 pi, so you have 3 pi. which is a different phase, but then it's 2 pi phase shifted with respect to the other component, so it's still going to add. And same thing, you can repeat, and you have 0 phase shift upon reflection, but pi by 2 over here. So if you look at that component, that will also have 3 pi, and so on. So you can have multiple layers, alternating layers of low and high refractive index, and you can essentially make a mirror. So this will be a highly reflecting mirror if you have more number of layers, right? And so the reflectivity depends on the number of layers as well as the index contrast between high and low refractive index. If there is a huge index contrast, then that would correspond to achieving, say, 99% reflectivity with less number of layers. On the other hand, if the refractive index contrast is low, you may need many more layers to achieve the same reflectivity. Okay, but that's the basic principle of a dielectric mirror, right? And now let's just examine this condition. We have assumed that there is a pi by 2 phase shift while propagating through this thickness. So let's actually look at that. So when you look at the phase that the light accumulates at say a particular wavelength lambda, that phase is given by 2 pi over lambda multiplied by NH is the refractive index of the high index layer. Let's say the thickness here corresponds to DH. Similarly, the thickness here corresponds to, let's say, DL. So 2 pi over lambda NH multiplied by DH is equal to pi by 2, right? If you work that out, you basically say DH is going to be equal to lambda over this 2 is going to come over here, so 4 times NH. And similarly, for the low index layer, you can also find DL will be equal to lambda over 4 times NL. Okay, and if that's the case, then we are talking about this entire thing corresponding to one high and low index pair. So let's have that overall thickness as capital lambda. That corresponds to the period of this structure. So if you look at capital lambda, which is DH plus DL, is going to be lambda over 4 times NH plus lambda over 4 times NL. Okay, so if you consider that NH is approximately equal to NL, if the index contrast is on the lower side, then you can effectively replace NH and NL by say N effective, and if we do that, then we get this expression capital lambda equals to lambda over 2 times N effective, which implies that you can write this lambda, which we now can call as a center wavelength, right? Instead of just calling this lambda, if you have that center wavelength is called lambda b, then you can just say lambda b equal to 2 times N effective capital lambda, right? So that so it works nothing. I mean, it's not any different from how a dielectric mirror works upon normal incidence. Why normal incidence? Because we're talking about light coming in here in an optical fiber. It's typically a single mode optical fiber, and it's incident normally on this grating, and the grating is actually reflecting light in this case. So the fiber Bragg grating behaves in a similar way as a dielectric mirror. Okay, so that is one way of explaining. Of course, the other way of explaining is actually through couple mode theory. Okay, so we can we can look into that a little more detail. But before we do that, I mean, this just gives you the condition for getting this lambda b, right? But it doesn't actually give us any information about what is going to be the reflectivity and what is the width of the reflection peak and so on. Okay, so let's look at that. So in order to actually determine those, you would have to use couple mode theory. So let's actually go into that and check that out. Okay, so essentially, if you look at couple mode theory corresponding to fiber Bragg gratings, FBGs in short, what we are looking at is you have essentially an index perturbation corresponding to the fiber Bragg grating. So essentially you have some change in refractive index like this. Right, so you have a periodic change in the refractive index. So if you express in terms of the refractive index, what we have is, let's say this is actually corresponding to the core refractive index, NCO, and at these regions you have a higher refractive index corresponding to the, compared to the core refractive index. Right, and it goes back to the core refractive index here. And this refractive index change, let's call that delta n. Okay, this could be a fairly small number, but what it's doing is essentially you have light at a certain wavelength, right? So let's just say this is if you are looking at the Bragg wavelength, then it's coupling a forward propagating mode to a backward propagating mode with the same wavelength. Okay, so that's what this is doing, and that is done through this grating structure which has a period of capital lambda. So in what we learn in couple mode theory is the fact that if you want to couple from one wave to another wave, okay, then you have to essentially satisfy a phase matching condition. So what is this phase matching condition? Well, you consider essentially the phase constant beta 1, which is loosely called as a propagation constant as well. So you have two waves with different propagation constants, and they need to be compensated by or one wave may need to be slowed down with respect to the other wave by this grating structure. So this grating structure is having a component, say you can call that as a wave vector corresponding to 2 pi over capital lambda. Okay, so if you want to couple from one mode to another mode, from one wave vector to another wave vector, you can do that by a periodic structure. So this is what Bragg diffraction is all about as well, right? So in this case, we are talking about coupling a core mode beta C naught, right? That's what this mode has, into a mode that's going in the opposite direction. So that is actually represented by minus beta C naught. So you have minus beta C naught. This is equal to 2 pi over lambda. And when you talk about the phase constant corresponding to the core mode, you can write it as 2 pi over lambda for this particular wavelength, lambda b times n effective, plus you have 2 pi over lambda b times n effective is equal to 2 pi over capital lambda. And so in this case, basically the 2 pi cancels, so you have 2 times n effective over here in the numerator, and then you interchange the terms, and of course what you get is lambda b equals to 2 times n effective multiplied by capital lambda, which is of course consistent with this other picture where we were just looking at the phase changes upon reflection. Okay, so you can essentially use either of those pictures, and you can show that this lambda b, the Bragg wavelength, is determined by 2 times n effective capital lambda. So if you come in with broadband light, you are able to pick up one particular wavelength, or rather it's actually a small spread of wavelengths around lambda b. Why do I say it's a small spread? Well, even if you are off lambda b, if you are slightly off from detuned from lambda b, this reflection still happens, right? All these points, the reflection still happens. It's just that they are not exactly in phase. So because of that, they don't add up as much as it does in lambda b. But that doesn't mean that there is no reflectivity. So the reflectivity is a finite value around lambda b. It just has a value less than the value at lambda b. Okay, so we want to actually find out how this reflection spectrum is going to look like. Okay, so that's what we will do next. And to do that, like I said, we need to probably go into a little more details as far as couple mode theory is concerned. So the basis for which we can actually write out here, so we are basically saying that let's say this is along the z direction. So you are going from z equal to 0, z equal to L is where this perturbation is present. And what this perturbation does is you have a incident wave, let's say with a field whose amplitude is given by A. So you say the field over here is A of 0, but as it propagates down the grating, it is getting depleted. Why is it getting depleted? Because at each of these interface it's getting reflected, so the original amplitude is now going to go down. So it basically goes down, let's say like this, right? And then finally it goes out with this value which you can write as A of L, right? Now what can you say about the reflected field component? Well, the reflected field component is going to let me just represent this in red. So the reflected field component is going to have start with a value of B of L, but it's going to actually increase as it's actually propagating, because it's coherently adding up with other field components. So it's going to run parallel to this line, and it's going to come out with B of 0. Okay, so now what is reflectivity? Well, reflectivity, if we were to define, so this is what we are trying to find out. Reflectivity is a value that's defined with respect to the power. It's the reflected power over the incident power. So this is basically B of 0. So the power is proportional to the magnitude of the field square. So this is what we want to find out, right? And this we want to find out at different wavelengths, essentially. Okay. And of course, there are some generic conclusions that we can make, or observations we can make based on this. We can say that the rate at which it's getting depleted depends on the index contrast between the high and low regions. So larger the index contrast, more will be the depletion. And of course, vice versa, if the index contrast is relatively small, as in the case of a fiber Bragg grating, that delta n is typically in the order of 10 power minus 4, right? If it's a relatively low index contrast, then you may need the depletion. The rate at which it depletes is not as much, but on the other hand, if you have a longer length, it will actually end up depleting more, and that actually means that you have more reflectivity. Okay, so you can make some observations like that. Now, the other observation you can make is essentially the boundary condition. The boundary condition, and at this side, you can actually say this B of L should correspond to 0. Let us assume that there is no other light coming from the other direction. So the only light that we are considering is actually incident from this direction, right? So if you consider that, and if you also you can also consider that the when we look at the reflection or the reflected power, it's not going to change with respect to the total reflected power is not going to change with respect to this direction. So you can write that d of z, the differential with respect to the z direction of b of z whole square, that corresponds to the intensity, but we can consider that's proportional to the power. So minus a of z, right, that is going to be equal to 0. So essentially we're saying that whatever reflected component you have is going to be because of the incident field components, the presence of the incident field component at that particular point. Okay, so you can that is another observation you can make, and that can help solve this this particular set of equations. Well, what we have is actually these couple mode equations, right? So we can write the evolution of the incident component, incident field component, as well as the reflected field component. It's going to be dependent on each other. Like the incident field component, the evolution is going to be dependent on the the reflected component, because of the fact that even as it's reflected, it's part of it is going to be reflected back, and that's going to add to the incident field, right? So it's going to happen in a continuous manner. So you can write dA over dz as minus I kappa a to b. That's actually what is called the coupling coefficient, multiplied by b times e power I delta z. I'll come back and define what delta is. That's clearly a phase term, phase modulation term that we have. And similarly, when you write, you can write the evolution of the reflected field, which is denoted by B, as minus A kappa BA, and that's actually dependent clearly on the incident field amplitude, A e power minus I delta times Z, minus I because it's actually going in the opposite direction. So by the way, all these are discussion from this book by Amnon Yariv. It's a book that's titled Optical Electronics, right, by Amnon Yariv. So you can find this discussion here, where we need to define two terms where you have delta, where delta is actually the detuning constant. Remember we talked about beta 1, beta 2 and 2 pi over lambda. So that is what this is representing. So you have beta A that corresponds to the propagation constant of the incident field, minus beta B, that's the propagation constant of the reflected field, minus 2 pi over capital lambda. So what can we say about delta at wavelength lambda b? At lambda b, we know beta A minus beta B equals to 2 pi over lambda, so delta would be equal to 0. So that's actually a special condition that we will look at. And we will also say that kappa AB is nothing but conjugate of kappa BA, right? So in terms of magnitude, it's the same, and because it's all happening in the same structure, and that is actually going to be given by the overlap of it's going to correspond to coupling due to some perturbation to the field. What is causing this perturbation? What here the perturbation is caused by this refractive index change. So when we talk about quantifying kappa, so this will correspond to omega times epsilon naught over 4 in double integral of delta n square, right, the refractive index perturbation that we have, multiplied by the field corresponding to the incident wave, field corresponding to the reflected wave, EA, EB, dx, dy. So that's actually integrated over all this dimension in the transverse plane, so that you can write it as minus infinity to plus infinity. But most of the action is happening around this core region. So even if you go a few microns from the core region, there's not going to be a significant field. But essentially this EA, EB, dx, dy, what it's denoting is actually the overlap integral. So it's basically the overlap of the two fields. Okay, and that overlap, as far as this structure is concerned, we can say is going to be fairly strong, because the both of these waves have to satisfy Maxwell's equations for this waveguide. So essentially we can say that if your incident field has distribution like this that looks somewhat Gaussian because it's a fundamental mode, the reflected field also is going to look somewhat similar, except that the overlap of the fields with respect to the perturbation is limited to only the fields within the core region. So that's where the delta n comes into the picture. It's limited only within the core region. The cladding, the fields in the cladding is actually not seeing this index difference. Okay, so you need to actually account for that in terms of a confinement factor. Let's say you have a confinement factor eta, which talks about how much of the energy is actually present in the core of the optical fiber. Okay, so we'll come back and look into that. Now we need to solve this with these boundary conditions, B of L equal to 0, and then you have to basically conserve energy in this structure, and that's what this is reflecting. So if you do all of that, I'm not going to actually go through the steps in the interest of time, but if you do all of that, you get an expression for the reflectivity of this grating, and that expression, so in terms of reflectivity, which we defined as the magnitude of the reflected field square divided by the magnitude of the incident field square. The solution for this is going to be in the in terms of hyperbolic sine and hyperbolic cosine. So essentially the expression for reflectivity will also be in that sort of manner. So this is going to be given by sin h square, kappa AB and kappa BA. Let's just represent that with a common kappa square minus delta square, the whole root, multiplied by L, where L corresponds to the length of this fiber Bragg grating, right, divided by cos h square root of kappa square minus delta square multiplied by L minus delta square over kappa square, where delta, as we talked about, corresponds to beta A minus beta B minus 2 pi over capital lambda, which is equal to 0 at lambda equal to lambda B, but it's some other finite value for any wavelength away from lambda. Where does lambda come into the picture here? Because beta A is given by 2 pi over lambda multiplied by n effective, right? So that's where the lambda dependence comes from. And kappa, if you evaluate for this structure, this can be approximated as pi times delta n divided by lambda multiplied by eta. That's essentially something that you get by evaluating this integral for this particular structure. And once again, I'm not going to the details of how that is done, but so that is how it works out as far as the coupling coefficient is concerned. And eta is actually your confinement factor, which we can assume to be a relatively large number as far as a well-guided fundamental mode is concerned. But if you go to a wavelength much longer than the design wavelength, which is around the cutoff wavelength, if you go to much longer wavelength, then we know the fields are going to extend much farther into the cladding, and in that case eta is going to be a number that's much smaller than 1, and if that is the case, then the coupling coefficient also is going to be relatively weak. Okay, so how does this all work out? Now this is actually the reflectivity. We can say reflectivity as a function of wavelength is like this, but if you are interested in the reflectivity at lambda equals to lambda b at the center wavelength, right, then we know at lambda equal to lambda b, your delta equals to 0. So if you drop delta, then this term, the denominator, goes away, and these terms would go away as well. So you just get a kappa times L. So this actually works out to be tan h square kappa multiplied by L. So that is one important result. And of course, if you want to evaluate this, if you want to get a feel for how this works out, if you say, for example, let delta n equals to 10 power minus 4, and let's say the length is typically 3 millimeter, right, and let's say lambda we are considering as 1.55 micron. Okay, if we use this, then if you evaluate kappa times L, that's going to be pi times 10 power minus 4 multiplied by 3 into 10 power minus 3 divided by lambda, which is 1.55 into 10 power minus 6, and this will work out to be a number approximately equal to 0.6, and if what that means is the reflectivity is work out to be something in the order of 30%. Okay, so how can you increase the reflectivity? So why is the reflectivity important? Because you are picking up this Bragg wavelength from any other background noise at the receiver, right? So higher the reflectivity, the better, but you cannot ensure high reflectivity over an extended period of time. So you should be able to work with even lower reflective gratings. But anyway, reflectivity. If you want to increase the reflectivity, what can you do? You can possibly go for higher index contrast, or you can increase the length of the grating. So we will look into some of those details in the next lecture.